Hey, everybody. We are now into chapter 11, which means that we are doing our intro to calculus um, unit now. And what we're going to be talking about really in this chapter is the idea of a limit and the limit concept, which is a fundamental concept of calculus. And we're going to be looking at it in the context of two really basic problems in calculus: the tangent line problem and the area problem. Um, So let's first get a general, really basic understanding of what a limit is, what it means, um, and then we will, go from there. So, kind of a way to express where this idea comes from is this type of problem. You're given 24 inches of wire. You're asked to form a rectangle whose area is as large as possible. What dimensions should the rectangle have? Now, this is the kind of problem that you would have done maybe in Algebra 1. It's a maximization problem. But it kind of forms a foundation for what we're doing here. So what you would have to do is kind of try and make an equation. You would say, well, twice the width plus twice the length is that 24 inches of wire. So that's perimeter. Is there anything I can do with that? I can manipulate it a little bit to get the length by itself. Which is, something. So now I can say length is expressed as W, and since I'm, talking about area and I want area to be as big as possible, I need an equation that actually involves area. So I say that area is length times width, but now I have width in terms of L. So when I multiply length, written in the way that, I just figured out by using perimeter, times the width, I can get a polynomial. Now, generally what you would be doing here is trying to look for the maximum of this quadratic. But what we're going to do is something a little bit different, which is just experimenting with the polynomial to figure out, where the maximum is. We're not going to look for the exact one, but we want to approximate it. Oh, and by the way, I'm listening to music because I feel like it, and hopefully that's not too distracting for everybody. So anyway, we're looking around and trying to find a specific, maximum area for this whole thing, and I'm realizing that as my width goes from 5 to 5.5 to 5.9, it's increasing still. My area is still increasing, from here to here to here to here. And the same is true if I go from 7 to 6.5 to 6.1 to 6. It looks like as I come from the left side, increasing in value, or come from the left side, decreasing in x values, then my area kind of seems to be approaching 36. So 36 is probably where that maximum is. But a way that I can say this in terms of limits is that the limit of the area function as the width approaches 6 is 36, and the way that we write that is down here at the bottom. The limit of the area function as w approaches 6 is, and then I can rewrite this instead of just having area. I can substitute what the actual function is, and I can say the limit of the 12w minus w squared as w approaches 6 is 36. Okay, so that's kind of just like, how do we say it? What do all these little symbols and things mean? Let's go and actually look at the definition and start looking into it. So what the definition formally is, and what you'll all probably never actually write this whole thing out because for whatever reason the symbols cause everyone to freak out. But if f of x, so if a function becomes arbitrarily close to some number L as the x values approach some other number c from either side, in the last example we were looking at it coming from the left side, coming from the right side, then we can say that it has a specific limit at as that x number approaches c at L. So basically what we're saying is the limit of x, as it approaches some number of the function f of x, will be the place it approaches if it becomes arbitrarily close to some unique number L. Let's see what that looks like in context, because I know it's kind of hard to grab onto at first. So what we're going to do is use a table to numerically estimate what the limit of 3x minus 2 is as x approaches 2. So we're looking to see if there's some arbitrary number that this function approaches as my x values get closer to 2 from either side. So my x values are going to get closer to 2 from the left, going 1.9, 1.99, 1.999, and they're also going to get closer to 2 coming from the right, going from 2.1, 2.01, 2.001. And let's see how the f of x values behave. Do they approach some number, the same number from both sides? This one is 3.7, 3.97, 3.997, so it seems like it's kind of approaching 4. This one's 4.3, 4.03, 4.003. So yeah, it looks like they're both approaching this arbitrary number 4 from both sides as the x values are approaching 2. So what can I say from that? Well, I can say, from the table, that it appears that the closer x gets to 2, the closer f of x gets to 4. So we can estimate that the limit of that function as x approaches 2 is 4. And the graph kind of, helps to support that idea. My x values were getting closer and closer and closer to 2, both from the left and from the right, and it was approaching 4. F of 2 actually is 4. So that appears to be correct. Sometimes that doesn't actually happen. Sometimes a limit will fail to exist simply based upon the type of function that we're looking at. For example, this function, the limit of the absolute value of x over x as x approaches 0. Now, at first glance, this function might seem a little bit difficult, but it's really nothing too crazy. If I put in any number into the top and bottom, it's going to be the same number, with the exception of the fact that the top will always be positive. So as x approaches 0, how does this function behave? Well, if I were to graph it out, this is what I would get. And it's a little bit, interesting, because I always have a number divided by itself, so it always gives me a 1, but depending on if I'm greater than 0 or less than 0, it'll either be positive 1 or negative 1. So from the left side, if I start approaching 0 and I say negative 2, okay, it's a negative 1. Negative 1, okay, it's a negative 1. Negative 0.5, okay, it's still negative 1. Negative 0.25, it's still negative 1. It looks like it's approaching negative 1. It's not going to move off of that. But if I approach it from the right side and I say 2, okay, it's at 1. 1. Alright, it's at 1. 0.5. Okay, it's still at 1. 0.25. Still at 1. It looks like it's approaching 1, and it's not going to change off of 1. The issue there is that I'm approaching two completely different numbers. I'm approaching negative 1 coming from the left side. I'm approaching 1 coming from the right side. So I'm not going to be able to get a specific arbitrary L value for a limit. There's not one number that both approaches from the left and from the right. Right, so what that does is that implies that the limit does not exist, and that particular graph is not continuous. Now this happens a couple different ways. We just looked at an example of the first way, which is when the particular function approaches a different number from the right side or the left side. So I was approaching 1 from the right, negative 1 from the left. For the second one, it's either increasing or decreasing without bound as we're approaching a specific value. Now what that looks like is something like a function that increases without bound there and decreases without bound there. Let's say this is our axis. So this is our y-axis, this is our x-axis. And I'd be looking for the limit of this function as it approaches 0. Well, as it approaches 0, this one's just increasing without bound. And as it approaches 0, this one is just going without bound. So they're never actually touching this particular point, and there's not going to be a limit. The last case is when it oscillates between two fixed values, and that would be something like, if you think about oscillation, the first thing that comes to mind is probably sine, cosine functions that move up and down and up and down and up and down. And that's exactly the thing. If I look at like the sine of 1 over x, that's going to be a one that does not have a particular solution, because it's going to look like this. And it's going to oscillate and oscillate and move off. So in here, as I try to say that there's a particular limit as x approaches 0, I'm not going to find it because it's moving and it's moving. It's never really approaching a specific arbitrary value. Okay? Now, what I'd like for you to try is exercises 35, 37, and 39. Basically what you're going to be doing there is just looking at a couple of different ones and saying, does the limit exist? And using these rules to say, does it exist or does it not exist? And hopefully we'll be okay with that, and I'll be able to check that over with you guys in class. Now, after you've done those, you want to look at some of the properties of the limits and how we can, sort of estimate or find them. First of all, just like we saw in that first example, where I think it was, what was it? It was a function, like a linear function. 3x gives the limit as x approaches 2 of 3x minus 2. And we found out that that limit is about 4. And the way that we can do that without having to, kind of plug in values and check is by direct substitution. Sometimes we actually can say that the limit of a specific function as x approaches a number is the same thing as actually f of that number. So this particular function is f of x equals 3x minus 2. In order for me to do direct substitution, I could say, it's supposed to be approaching 2. Well, what happens when it is f of 2? Well, that happens to equal 4. Okay? That is my limit. Because the particular function exists at that place, and there is a point, then the whole graph is continuous, I can directly substitute and say that the limit of that function as x approaches c is f of c. And there's a lot of these really what are considered well-behaved functions. And it's not just linear functions, polynomials as well as rational functions, bearing that there's no 0 in the denominator. They all they can have this type of property. And there's a couple of other interesting things about direct substitution and limits. If I have the limit of a function that's just a number, like I'm saying the number is b here, so like say, actually I think I have examples on the next page. So something like the limit of, not there, never mind, we'll do the examples later. So if I have the limit of a specific number as x approaches c, it's just going to be that one specific number. If I have the limit of a particular function as x approaches c, then it will be just the c value because of the function x. If I have the limit of x raised to a specific power as x approaches c, it'll just be that c value raised to the power, and the limit of a function within a square root or some sort of nth root as x approaches c will be the nth root of that c value. And these will be a lot clearer when we see them with examples. I know that looking at the symbols doesn't really make the connection very strong for you at this point. Now this page, I'm sure, kind of makes everyone freak out a second, but I promise you that in about 2 minutes you're going to think that this page is one of the simplest things you've ever seen. Basically, what we're looking at here are some of the easiest properties that you've probably seen all year. And all it concerns is that we have a specific limit as x approaches c of f of x, and a specific limit of x approaches c of g of x. So we're saying the limit of this function is L, the limit of this function is K. Now we can look at a couple of properties. And basically what we're saying here is that if I have a limit of a function that's being multiplied by a number, then that's going to be the same thing as that limit of the function times that same number. So it's just a scalar multiple. So the limit of b times f of x is the same thing as, just the limit of f of x times b. So that's a pretty, nice type of scenario. The next one is saying if I have the limit of two different functions that are being added or subtracted, well, that's the same thing as their limits added or subtracted. Alright, so again, that's like, it's almost too easy to say, okay, I have the limit of these two things, they're being added together, that's really complicated. Well, actually, no, it's not, because I can just take the limit of this one and add it to the limit of this one. No big deal. The same thing is going to be true for product. I have the limit of two different functions that are being multiplied together. That has the potential to be, pretty crazy. But it turns out it's just going to be the limit of the first times the limit of the second. Same thing is true for quotient. Function divided by a function, that's equal to the limit of the first divided by the limit of the second, provided that this denominator doesn't equal to 0. If it equals to 0, then there's a whole different story. But this quotient property, actually, we'll see again when we talk about rational functions, because rational functions technically are just a function divided by another one. And then lastly, if I have something raised to a power, a function raised to a power, it'll just be that limit raised to that power. Now let's look at examples. Right here I have direct substitution, right? I'm looking for the limit of, x squared as x approaches 4. Well, what actually happens to that function at 4? If I plug in a 4, I get 16. Well, the limit as x approaches 4 of x squared is 16. Easy enough. Now what about the limit as x approaches 4 of 5x? Well, I could direct substitute, or I could think of this like two different functions. It's 5, a scalar multiple of the function x. And I know the limit of the function x as x approaches 4 is just a 4. So I can multiply that by 5 and get 20. Simple enough. Now this one, a little bit trickier. It's the quotient property. I have tangent of x being over x. So I have two different functions going on here. But all that means is I have to take their limits separately. Limit as x approaches pi of tangent of x, and limit as x approaches pi of x. Now I can do direct substitution. I can substitute pi in here, see what I get. Tangent of pi is 0. And limit as x approaches pi of x, substitute pi in there, I get pi. 0 over pi is 0. Almost to the end, we have the limit of the square root of x as x approaches 9. Well, again, I can direct substitute, throw in the 9 in there. Square root of 9 is 3. Easy enough. And on this page, last one, I have the limit as x approaches pi of x cosine x. Well, again, this looks like it's going to be difficult. However, I have two functions that are multiplying each other. Simple thing is, I can just separate them. Limit of x, limit of cosine x, and multiply them together. Direct substitute in here, I get pi. Direct substitute in here, I get cosine pi. Pi times the cosine of pi gets me negative pi. Boom! And last example, we have a couple of different things happening here. I have the limit as x approaches 3 of x plus 4 squared, which, again, you're thinking, what? Craziness, I can't do it. I'm stopping. That's it. I'm going home. I don't care anymore. No, wrong, false. You can do it. There's just a couple of different things happening. I have addition on the inside, which means I just take this one separate from this one, and then add the two limits together after. And then I have an exponent on the outside, which, again, means I take the limit and then square it. So, I'll go from the inside out. What is the limit of x as x approaches 3? It's a 3. What's the limit of 4 as x approaches 3? It's a 4. Now I can worry about the squared, because I had to square those limits afterwards. This in here becomes a 7. 7 squared is 49. Easy as pie. And this is what I was talking about with rational functions. Again, the mumbo jumbo in here is going to get you confused, but essentially all we're saying here is that rational functions are going to follow that quotient property. So you're going to have a function on top of another one, which is just going to imply to you that as long as the limits of both exist and the denominator one is not a zero, you have a limit there. Okay? What I would like you to try is exercise 51. It's got multiple parts in it, but it basically wants you to use some of those direct substitution properties in finding some limits. Hopefully by the end of that, we'll have a pretty fair understanding of how to calculate or estimate these limits, and we don't get too freaked out with the new vocabulary, the new symbols and whatnot. So good luck with those. I'll talk to you guys in class next time, hopefully clear up any questions, and we'll